So I've never actually worked at Stanford, but I had the pleasure to interact with Shoucheng roughly 10 years ago, and also with Zhang and Sri. And basically we are together as authors on 2 papers. And of course I was always struck by his generosity and kindness as a human being, besides the intellectual capacities that everybody described. In this session, the title of the session is Strongly Correlated Electrons, and the first speaker is Joseph Maciejko, or maybe you have to pronounce your name again, that I learn it. And yeah, he's going to talk about disordered and deconfined exotic quantum criticality with Dirac fermions, and I will try to give you a sign after 20 minutes, then you have 5 minutes left to talk.
Okay, so thank you, Carson, for the introduction. So yes, I'm Joseph Maciejko. I was a PhD student with Shoucheng between 2006 and 2011, and I just feel really lucky and privileged to, have been in his group and have been able to work with him and many of his brilliant collaborators like Zhang, Taylor, and Sri, and many others. And really, I'm happy to be here to be able to celebrate his scientific achievements and his life. And so for me, Shoucheng was, of course, a brilliant physicist, a role model, but also a very devoted mentor and a very kind person who really kind of took to heart this work of mentoring us and really helping us to become the best physicist we can be. And one way he was doing that, and I think it's been mentioned in previous conversations, is that he would ask us to teach him things. And so in my case, he asked me to teach him the Gapless formalism, which is something I had worked on as a master's student in Canada at McGill. And whenever we were teaching things to him, he would always remind us to use the blue pen. That was an important thing, to have the good contrast whenever we were doing derivations on the whiteboard in his office. So I like this picture because it reminds me of that, and it's sort of one of these fond memories of discussing physics with Shoucheng. And so I just wanted to read a quote of something that he wrote. We heard many quotes by Shoucheng. And this is from a beautiful essay that he wrote for a festschrift organized for John Wheeler's 90th birthday in around 2002. And it's, the title is taken from this poem from William Blake that we heard about. And it's a beautiful essay. And for me, this is really something that sort of drew me to his work and his vision of emergence in condensed matter physics. So I'll read it. So he says, atoms, molecules, and quantum liquids are made of elementary particles at very high energies, but at low energies, they interact strongly with each other to form quasi-particles, which look very much like the elementary particles themselves. Over the past 40 years, we have learned that the strong correlation of these matter degrees of freedom do not lead to ugliness and chaos, but rather to ordinary beauty and simplicity. And so I think it's very fitting that we have a session on strongly correlated systems at this memorial workshop. So we heard a lot about Shoucheng's contribution to topological band insulators and the beautiful physics of non-interacting systems. But of course, Shoucheng contributed a lot to correlated systems, whether theory of high TC, superconductivity, or fractional quantum Hall physics. And so as a small tribute to his vision and his work in both areas, I'll talk a bit about my own work in recent years, kind of trying to combine aspects of band topology and correlations and the physics that hopefully can be beautiful and simple that comes out of that. And so I'll be focused on Dirac fermions in condensed matter physics. So I'll be focused on the case of two-dimensional Dirac fermions. As we know, they can occur in many contexts in sort of non-interacting Fermi systems like semimetals. And of course, again, thanks in great part to the work of Shoucheng on the surfaces of three-dimensional topological insulators. But also, they had been known in earlier contexts as essentially weakly, again, interacting fermionic BDG quasi-particles in D-wave superconductors, and also the surfaces of topological superfluids, such as helium-3b. So they're not Dirac fermions in the sense that they don't have any charge, but they have this conical Gapless dispersion relation, which is just all I want to point out here. And so in all these cases, these Dirac fermions are not there at high energies, but they emerge as quasi-particles at low energies in the band structure or the effective band structure. But Dirac fermions can also be emergent in a different and maybe a bit more exotic sense. They can show up as emergent low energy excitations in systems that do not have any fermions to start with. And so this is the context of spin liquids. So for instance, in the case of the K-spin liquid, in which there's a lot of excitement due to the fact that it might be realized in this material alpha ruthenium chloride. And so there's this very beautiful model by Kitaev that says that in some range of the phase diagram, there should be a gapless fermionic excitation with some Dirac-like dispersion. Again, they're Majorana fermions, but they have this sort of Dirac-like dispersion. And there's also a belief that one might have sort of complex, more regular Dirac type fermions in quantum antiferromagnets on the Kagome lattice. This is the concept of the Dirac spin liquid, and the low energy physics is described by two-dimensional Dirac fermions and interact via emergent gauge fields. So in both of these cases, because the Dirac fermions emerge in a system that does not have fermions in its microscopic Hilbert space, these fermionic excitations are always coupled to emergent dynamical gauge fields. So in the case of the Majorana system, these are Z2 gauge fields, and for these Dirac spin liquids, they're complex gauge groups U1 or SU2 gauge fields. And so the main question that I would like to ask in this talk is, what happens if we take these Dirac systems and we turn on some strong interactions between these Dirac fermions? Okay, so I have this idea that we would turn on some sort of 4-fermion two-body interaction, and what type of physics can happen. And so as was pointed out in a previous discussion, I think Duncan was mentioning this, and Steve forgot the original context of the discussion, but if we have a Dirac fermion, so if we consider, for instance, a semi-metal like graphene or the surface of a topological insulator, and I will be focused on the case where the Fermi level is at the Dirac point, so it's really a semi-metal, it's not a metallic system. So if we imagine turning on some interaction strength between these fermions, then because the density of states vanishes at this Dirac point, nothing happens for a while. This phase is perturbatively stable against these interactions, but if the interactions become very strong, we expect there should be some sort of strong coupling physics happening, maybe some spontaneous temperature breaking. And so at zero temperature, there is bound to be a quantum phase transition. So it could be first order, but if we're lucky, it might be a continuous transition. And we would like to ask, besides asking what types of phases can be realized with strong interactions, what would be the universality class of these putative quantum critical points? So let me mention a few examples that have been discussed before. So the first would be what is sometimes called Dirac-Mott quantum criticality. So the basic idea there is that you start from a Dirac semi-metal like graphene, and then, or more generally, you can think about some model on a honeycomb lattice with n flavors of electrons. So you might have a certain number of these Dirac fermion flavors that is proportional to the number of electron species on the lattice. You might think of some, let's say, cold atoms realization where you can tune this n potentially or have large values of n. And then if you turn on a certain type of interaction, then you can show either using sort of mean field calculations or perhaps more convincingly, there's some very nice Monte Carlo simulations done by independently by, in fact, Konjung Wu's group and also Hong Yao's group, where they see a direct continuous quantum phase transition between a semi-metal to an insulating phase where there's this K-Coulé valence bond pattern where some of these bonds become stronger, and this breaks the point group symmetry spontaneously, and this opens up a gap in the Dirac dispersion. Okay, and so so if we think about the system perhaps closest to reality, a system with two species, basically spin up and spin down fermions on this lattice, then this may perhaps be relevant for graphene, and there's perhaps evidence that this, at least this K-Coulé pattern has been observed in experiment. And so what I would like to ask about is what are the universal properties of this quantum critical point? Okay, so in order to answer that question, we should formulate some Leonard Ginsburg Wilson theory near the critical point. So we need to identify the order parameter. So there's this valence bond order parameter, very similar to what Subir was mentioning. It's a, yep.
You're saying that you put Hubbard model on the honeycomb, there's a VBS phase before you get the antiphone. Is that the latest?
This is the, yes, so for n equal 2 for this, but this is not the on-site interaction. This is a bond interaction. It's not the regular Hubbard. Yeah, that's right. Otherwise, this is a direct transition to the antiferromagnet. Yeah. So this bond interaction favors this K-Coulé phase. And so, as Sabir pointed out, this, the VBS order parameter in this system also turns out that at long wavelengths it really is it's an XY type vector. There's really some anisotropy because it's a discrete point group symmetry that is broken spontaneously, but near the critical point it turns out this anisotropy becomes irrelevant, and so the sort of Leonard Ginsburg theory is that of an XY order parameter, but it turns out that it's very important to keep the coupling between this order parameter fluctuations and the gapless Dirac fermions, and in fact this will change the universality class of the transition. Okay, and so we can see that because if one looks at the critical exponents, for instance, the correlation length exponent, so it's been studied in quantum Monte Carlo. This is results from Hong Yao's paper, and also in field theory. It's very clear that the exponent nu is quite different. So it's about 1, and it depends on the number of fermion flavors, and it's quite different from the pure 3dxy universality class. Okay, so basically the coupling of these fermions to the order parameter fluctuations changes the universality class. Another characteristic feature is that you typically get large anomalous dimensions for the order parameter field, which is compared to, let's say, these pure bosonic theories, and this reflects the fact that order parameter fluctuations can decay via low order processes into electron hole pairs as compared to these higher order processes in the purely bosonic theory, and this is reflected in these large anomalous dimensions. I'll mention just very briefly in passing, there's some recent work that claims that maybe this transition can be seen, at least numerically, in models that may be relevant for these twisted bilayer graphene systems. And the last example that will be relevant for what I'll be talking about later is so this time not a semimetal to insulator transition, but a semimetal to superconductor transition. And here I'll be focused on the case of a single Dirac fermion. So there is some interest in this for a variety of reasons. So actually this kind of ties into the talk by Dong Hai. So the question of, first of all, can you simulate a single Dirac fermion with time reversal symmetry on the lattice? And so this was pointed out by this, again, this very nice work by Hong Yao that, so you can do that, but of course you have to violate one of the assumptions of the theorem discussed by the previous speaker, which is this, the assumption of finite range hopping. So what Hong did was to consider a model with long range hopping, and then the dispersion relation is actually discontinuous near a Brillouin zone boundary, but you can do that in finite size. You can study this, and you see a continuous corner critical point for essentially a Hubbard model with this long-range hopping type binary model and attractive interactions, and you see a transition into a superconducting state. So again, the critical exponents are different from those of the pure 3dxy. Probably even though the symmetry that's broken is U1, it would be the same. The exponents are different. I just, again, briefly mentioned in passing, there was an experiment a few years back that seemed to suggest the observation of intrinsic surface superconductivity on the surface of a single Dirac cone, 3 topological insulator antimony telluride, which was also predicted originally by Shoucheng and Shidai and collaborators in 2009. So maybe this transition perhaps can be seen in an experiment, although this experiment has not been reproduced so far, so we don't really know. So I'll just mention one thing, that these quantum critical points with fermions, the fermions generically acquire also some anomalous dimensions, so there's sort of non-firm liquid behavior. And in this particular case, there was something that was of interest to some of us, which is that actually there is an emergent supersymmetry at this particular critical point, but I won't really say much more about that. So the main questions I would like to ask in this talk is how are these universality classes affected by two effects? So one will be disorder. So again, partially motivated by just a purely theoretical question, but also in the experiment that I briefly mentioned. If you do STM on this system, you see at low temperatures essentially some BCS gap developing, but it's highly spatially inhomogeneous. So clearly there is some disorder in the system. And going back to my first few slides, in these Dirac spin liquid systems where, we have Dirac fermions, and we can imagine thinking about symmetric breaking of these Dirac fermions with strong interactions, but now there's an emergent gauge field that couples these Dirac fermions, and how do we describe quantum critical phenomena in these systems with these emergent gauge fields? Okay, so this is the outline of the talk. So I'll talk about this, the first problem, which is the effective disorder on one of these quantum critical points. And then if I have time, I'll say a few words about the problem with direct fermions coupled to gauge fields. Okay, so this first work was done in collaboration with my PhD student, Gennady Ryzhakov in Alberta. So when we are talking about the disorder, we need to remind ourselves a few general considerations about the effective disorder in near phase transitions. So the problem that I'll be considering will be this Dirac semi-metal to superconductor transition that I just mentioned, but I'll consider a more general model that has n flavors of two-component direct fermions, n equals 1 corresponding to the topological insulator surface, and n equals 4 would correspond to graphene in this case. And I'll be adding quench disorder to this problem and asking how this affects the critical physics. So the first question you should ask is, if you add disorder, does the transition remain sharp in the presence of disorder? So if it doesn't, I'll take this as saying that things are kind of boring. If the transition remains sharp in the presence of disorder, we should ask, Steve seems puzzled.
How can it go to a superconducting state without a sharp transition?
Well, no, so, oh, you mean in the experiment?
No, conceptually. That's a broken symmetry state.
Yeah.
Doesn't there have to be a first place where you break the symmetry?
No, I'm just asking if I had quench disorder, whether the superconductor transition remains sharp. Yeah, in this case, yeah, for sure. Right, the symmetry has to be broken. Well, whether the transition happens at all, I guess, is the question. Yeah. And then, yes, that's really what I meant to say. So if the transition remains, is it still continuous? If it's not continuous, I won't be interested in that. Let's say it becomes first order. If it remains continuous, then we can ask, is it a new universality class, or is it the same physics, meaning disorder does nothing? So if disorder does nothing, that's not interesting. But perhaps if we're lucky, disorder can give rise to new universality classes of transitions. Okay, so when we talk about disorder, we should specify what kind of disorder we're considering. So in the context of symmetric breaking, there's two main types of disorder. There's a random field disorder and the random coupling disorder. So the random field disorder will be disorder that for which a disorder realization explicitly breaks the symmetry that the system is trying to break spontaneously. So for continuous symmetries, such as the U1 symmetry of the superconductor, then in general, if you have a continuous symmetry, that we know that this random field disorder will destroy long-range order in any dimensions less than 4. On the other hand, we have the random coupling disorder, which would be disorder that any realization of disorder preserves the symmetry that the system is trying to break spontaneously. And in the case of our superconducting system, an example of this would be this sort of local TC type physics, which could be modeled by a spatially varying effective BCS coupling constant. Okay, so in our problem, thankfully, for a superconducting transition, a random field, a random potential cannot break particle number conservation, so it cannot couple linearly to the order parameter, and therefore we can ignore this random field disorder. It's not there. And so we'll be interested in essentially looking at the effect of random mass or random coupling disorder near this Dirac semi-metal to superconductor transition. And so the model that we'll be considering is basically the same Lagrangian I had before, but for the bosonic piece of the Lagrangian, now I will have a random mass for my order parameter fluctuations. And then there's the fermions. Okay, so the general statement that we can make is, first of all, looking at the Harris criterion. So I don't have the time to explain the Harris criterion, but basically it's a criterion that tells you whether you expect disorder to change the universality class or not for this random mass disorder. Okay, so in this context, the criterion tells you that the quantum critical point, the clean quantum critical point, will remain stable against disorder provided that the correlation length exponent of the clean system is greater than 1. So it would be d over 2, where d is the spatial dimension here. D is 2, so we get 1. Okay, so we can look at the result that I mentioned earlier, either from the Monte Carlo simulations or the field theory, for different values of this number of fermion flavors. Okay, so for n equals 1, consistently we obtain a value of nu that is less than 1, and therefore we expect the critical point to be unstable to disorder. For a larger number of Dirac fermion flavors, So there is a bit of disagreement. It's actually close to 1, so it's a bit of a subtle question. If you look at the Monte Carlo results, which are non-perturbative, maybe you should trust those more, then it would seem to say that the clean critical behavior will be stable against disorder. Okay, so if it's unstable, then does that necessarily mean that the transition disappears? So that's the first question. And then, in fact, even if the transition is stable against disorder, does that necessarily mean that nothing interesting happens? Okay, so that's the question I'd like to ask. And so, despite this Harris physics, we'll actually revisit this problem and do an explicit calculation. So what we'll be doing here, first of all, is a field theory approach. So first of all, we need to average over disorder. We'll use the replica trick, which is a standard technique. And we'll do a renormalization group calculation. And so to control the renormalization group flow, we need a small parameter. And so we'll use the epsilon expansion. But in the presence of disorder for these quantum critical systems, it turns out to be convenient to use this so-called double epsilon expansion. So we'll work in 4 minus epsilon space and epsilon tau time dimensions, and we'll consider epsilon and epsilon tau to be small parameters. Okay, so this was first introduced by these authors in the context of random classical magnets. Okay, so we have these set of diagrams. We work at one loop. And to give us a bit of confidence or hope in this method, I'll just point out that if you look at the purely bosonic limit of this problem, which reduces to the random TC or random mass O2 vector model, there's actually good agreement of the results obtained by this method, even at one loop, with quantum Monte Carlo studies of the corresponding problem, which is the boson superfluid to Mott glass transition. So we'll take that as a license to use this approach for this problem. So I'll just mention the results. So if we first look at the case of a single Dirac fermion, so in the absence of disorder, we recover the known physics. So we flow away from the Wilson-Fisher fixed point. We go to this sort of fermionic supersymmetric critical point in this case. And then the RG tells us that if we do the analysis, disorder is relevant. And there's a runaway flow, and that's consistent with Harris. And we can't really see anything because the perturbative RG fails. If we go to n greater than 1, so 2 Dirac fermion flavors or more, what we find, again, consistent with Harris, is that the disorder is perturbatively irrelevant. So we might say, OK, well, nothing interesting happens. We go back to the same universality class. But in fact, I would say it's not the end of the story. What we find actually is that there are finite disorder fermionic critical and multicritical points, which are found, again, in the context of the epsilon expansion. So these are, for small epsilon, these are perturbatively small. So it's a controlled study. So basically, there is a separatrix beyond which the transition is controlled by a new finite randomness fixed point. Okay, so the schematic phase diagram would be as follows. So along the x direction, there's R, the parameter which tunes the semimetal to superconductor transition. And on the x-axis, we have disorder. So in the absence of disorder, what we find is that the critical physics is described by this clean fixed point. But if disorder exceeds a certain critical value, then the transition is controlled by a new critical fixed point. All the fixed points in the system obey the Shoucheng inequality. So if you will, once disorder is taken into account, they are stable to the addition of further disorder, if you will. And by contrast with the clean critical fixed point, which is a sort of relativistic type fixed point, which has dynamic critical exponent equals 1, these disorder fixed points actually have a z that is not equal to 1. It's still universal, but it reflects the fact that the disorder breaks Lorentz invariance, and the system reaches a compromise. The correlation time and correlation length diverge with different exponents that are related by this z here. And I'll just mention that if you indulge me in looking at large numbers of fermion flavors, perhaps cold atoms can help us in this regard if we're lucky in terms of experiment, then the type of the structure of the RG flow changes a bit. The critical fixed point describing the transition for sufficiently large disorder above this critical line actually becomes of stable focus type. There's a spiral type flow, and our RG eigenvalues, the leading eigenvalues are irrelevant, but they have a non-zero imaginary part. So there's a spiraling flow, and it was shown by Chmielnicki in the 70s that this type of flow would lead to oscillatory corrections to scaling. So in addition to the standard corrections to scaling exponent omega, which is universal now, which corresponds to the real part of these eigenvalues, now there's a second exponent exponent omega double prime, which gives an oscillatory piece to these corrections to scaling. Okay, so I'll just say a few words. I'm nearly out of time about the second topic, just to give you a flavor, which is sort of applying some of these ideas to the problem of transitions between Dirac spin liquids and either conventional ordered states or gapped topologically ordered spin liquid states. Okay, so this is work done with my current postdoc, Rufus Boyack, former postdoc Zhang Lin, Nikolai Zerf as a particle physicist. He's in Berlin. Ahmed Ryan was a student with me, and then Peter Markert, also a particle physicist in Germany. Okay, so this audience does not need an introduction to spin liquids. They are systems of local moments that do not order magnetically down to the lowest temperatures. They come in two great varieties, gapped and gapless. In the gap spin liquid family, the nice thing is that we have proofs of principle. We have exactly solvable models that tell us that these states can exist in principle. And we can get Z2 or chiral spin liquids. In particular, there's a lot of excitement regarding this one due to certain experiments, again, in alpha ruthenium chloride. Now, if we think about gapless spin liquids, the situation is a little bit murkier. So there's a lot of experiments that seem to point towards the observation of gapless spin liquids in nature. It's highly controversial. There's recent experiments that seem to contradict the fact that we might have gapless mobile carriers in this material. Okay, so, but even if we go back and look at proofs of principle, actually it's a very hard problem. So if we restrict ourselves to U1 spin liquids with a dynamical U1 gauge field, as far as I know, there's no exactly solvable model that, maybe Subir has one, I'm not sure, no, that gives us a spin liquid with a U1 spin-on Fermi surface or a Dirac spin liquid. Okay, and so I'll just say a few more words and I'll stop. So about this Dirac spin liquid here. So in that context, I think there's a really interesting piece of work with which Chenka, she was involved, that appeared last year. It was published very recently, where it's not a spin model, but it's close. So it's a model of fermions on the lattice interacting with a dynamical lattice U1 gauge field. And what they find, as they tune the number of fermion flavors, which translates eventually to a number of Dirac fermion flavors, is that there's a U1 deconfined phase in a finite range of interaction parameters in which correlations are power law, and that seems to be consistent basically with the Affleck-Martin pi-flux phase, but with a fluctuating U1 gauge field, not an SU2 gauge field, and with power law correlations that seem to agree with earlier field theory calculations on this phase. So for my interest, so that's already very interesting, but what's even more interesting perhaps is that they also observe a quantum critical point between this deconfined phase and an AL ordered phase. And furthermore, it seems to be continuous. So I'll just say that we can construct a field theory of this transition, which looks very much like this Gross-Neveu type theory, but now the fermions are coupled to a U1 gauge field. We find a stable critical point. We can compute exponents. We hope to compare with Monte Carlo in the near future. And then I'm out of time, but I'll just say that in this context, there's also an interesting duality relating the Néel-VBS critical point that Subir mentioned and one of these fermionic theories. And if we do large N calculations, we seem to find some evidence that corroborates this duality. But I'm out of time, so I'll stop here. And these are my conclusions, and I'm happy to take any questions. Thank you.
I see a question there in the back. Where's actually the second microphone? Or there used to be two? Somewhere. He has it, okay.
I'm a tad confused about what you think, going back to the first half of your talk, what the phase diagram is as the disorder increases. So there was one set of the parameter region where the conventional fixed point is unstable. And I can't see any change to the phase diagram there.
Okay, so this is just saying that the two phases are, I believe, the same, but the transition becomes, the universality class of the transition changes. So basically the semi-metal to superconductor transition is across those lines. But let's say if you had a clean system, the transition would have this set of exponents, and the system was more disordered than this threshold value here. it would be described by a different set of exponents. That's the claim.
I think Steve?
Yeah, I was also going to ask about the same thing. So are we sure that there's no differences in the phases? I mean, this is strange to have two different universal transitions between the same phases. It would sort of be easier to understand if it was some sort of multi-critical
Right,
point.
and then you had some dotted line here, right?
Yeah.
Yeah, so all I can say here is that in the semi-metal phase where the you have this random boson mass, so the order parameter is gapped, and so I don't expect that the physics of the semi-metal here will change.
Can't there be something of localization or finite density of states?
Yeah,
or-
that's a very good question. So something I didn't mention is that we assume that for these results to hold, we require that the disorder preserves particle hole symmetry. So this would be something like a random bond type disorder. So the basic idea is, you really should think from a system that has fermions and some random potential, right? And then the random potential that the fermions live in will generate all kinds of random couplings. In this particular RG calculation, the only randomness that turns out to be relevant in the RG sense is the random boson mass. Okay, but yes, I agree. So here would be something like a Dirac fermion with a random mass disorder, and random mass disorder in 2+1 dimensions is irrelevant. And it's not like the random chemical potential where you do generate a finite density of states. So I would tend to say that the Dirac semi-metal phase here is it's a disordered semi-metal, but the density of states remains
perturbatively irrelevant.
Perturbatively, yeah.
Yeah, but you're now at finite.
Correct. So
disorder.
that's why basically the simple answer is I don't know, because we're doing some RG where this parameter R grows and then you lose control of the RG. So it would be nice to have some other way of understanding, maybe some large N or some mean field that would enable us to understand what is the nature of the phase finitely away from the critical point. I agree.
For the case of n equal to 1, so the disorder is Harris relevant.
Yes.
So what is the fate of this fixed bond? Does that flow to an infinite random disorder?
So so you're asking about the specific direction, right? So I'm forgetting now. So in this particular analysis, we find it's a bit of an artifact of the calculation. It's marginally relevant, even though from non-perturbative determinations of nu, we know it should be relevant, not just marginally relevant. The direction, yes, basically, I mean, in this one loop calculation, this sort of flows to a strong disorder. So there's not much we can say, I guess.
Okay, the very last question here. And we have to move on.
A quick question. So, does it make a difference if it's Dirac fermion or Dirac fermion for the disorder?
It's a good question, yeah. So we haven't studied the Majorana case. Definitely, that's something that's on our to-do list. Yeah.
Okay, so thanks, Joseph, again.